I'm going to tell you about some work we've been doing on using refinement types to secure web applications. So we trust web applications with all manner of sensitive information about our lives, our professions, our finances, our health, and it's not clear that this trust is entirely warranted, as glitches in these applications are routinely exploited to exfiltrate sensitive data. Why do we have these glitches in the first place? Well, the trouble is that typically the people who design these applications do think about security, but the mechanisms they have for enforcing it require them to sort of sprinkle a whole bunch of checks inside their code. So the security is sort of intertwined with the business logic, which makes it really hard to determine whether the checks have been sort of implemented correctly, or even whether there is some high-level security policy in the first place that's even being implemented. So what we wanted to do in the Storm web framework is to separate the policies from the quote-unquote business logic, right? What we want is to have some standalone notion of a security policy that is easy to audit and trust, and then have some systematic way to automatically verify that that policy is actually properly enforced throughout your web application. So having motivated why we want to secure web applications, I'm going to give you a kind of high-level demonstration of how you build applications with Storm. And then in the last part of the talk, which is really the bulk of it, I'll give you an overview of how Storm enforces security via refinement type checking. So let's start with a high-level overview of how one would use Storm. So imagine I want to build a kind of a wish list application where everybody has their, users have their list of things they would like their friends to buy for them, for example, on their birthday. And some wishes might be public. I might want everybody to know, for example, that I love Godzilla vs. Kong because you know what? It's a great movie. And there are other things maybe I don't want everybody to know. For example, that I love karaoke. I might want to keep these things private. I might imagine a policy for this web application that says that only the user who owns a particular wish should be allowed to access the private wishes. The public wishes, anybody should be able to see. We are going to start with the database schema that is sort of very common and ubiquitous in web applications. So this database schema essentially declares the different tables that the database stores. So there's going to be a table for each user, and the table, each row is going to store the user's name and their email, both as strings. And then you might have a separate table that stores wishes. So for each wish, we're going to store the owner of that wish, so an ID, a pointer to whoever the user is who owned that wish, a description of that wish, perhaps its title is a string, and perhaps a level which might be public or private, which determines who should be able to see that particular wish. Now the policy we might have might say something like this, right? Remember, the policy was only the owner should be able to see a wish unless it's marked public. And this predicate is going to return true if either the level field of that wish, okay, this level, is the string public, or the owner of that wish is exactly the same as the viewer. Okay, so notice these are data dependent policies. The policy depends very much on the data that's stored in the database. And this is essential for sort of writing real world realistic security policies. What I'm going to do now is I'm going to take this predicate and I'm going to attach it to this wish, to this row of the wish table. And it's going to say that the titles or the descriptions should only be visible to the owner unless they're explicitly marked as public. Now let's look at an example application. Okay, so here's a snippet of the web server perhaps that returns the list of wishes that belong to some arbitrary user UID. So in the first part, what the server is going to do is it's going to create a query that looks for all the wishes that belong to UID, whose owner is UID. Then it's going to execute those wishes using this select operator that runs the database query. And then having obtained the wishes, it's going to pull out the description. Maybe we don't want to send all the information, just the descriptions. And then finally, we're going to send back a JSON or text or HTML response with all the titles. Now Storm is going to reject this code and is going to complain that there's a leak over there. Why is there a leak? Well, if you look at the security policy, this returns all the wishes that are owned by UID, and those should only be viewable by UID. We have not checked whether or not they're public, right? And so now since these titles are only viewable by UID, and since the response is sent back to the current session user who might not be the same as UID, Storm is going to complain and say, sorry, this code does not respect the security policy. How might we fix it? Well, what we want to do is to restrict the query to take only the public wishes when the session user is not equal to UID. Okay, if the session user is the same as UID, then it's fine to give the person back all of their own wishes. So here's how we might do that. I'm going to get the viewer. I'm going to sort of query Storm to say, hey, who is the viewer right now? Who is the session user? And then I'm going to compare viewer to UID. So if viewer is the same as UID, then I do nothing. Otherwise, I add this extra conjunct to my query that says level equals public. Okay, and now I'm going to update my query to owner equals UID and this extra conjunct query. Okay, and effectively, this is going to restrict the results to only the public users, public wishes when the session user is not equal to UID. And now Storm says, okay, well then in that case, this code satisfies your security policy as declared at the outset. So having given you this high-level demonstration of how to secure apps with Storm, let's now dive in and see how Storm actually enforces security. At a high level, what we want to do is let's look at the anatomy of the web server. Let's see what its elements are. Okay, so if this is the entire code of the web server, as Haskellers, what you will have noticed, of course, is that this whole thing is a giant do block where each server is comprised of a whole bunch of smaller atomic actions, which you can think of as computations glued together as with bind and return and so on. Let's drill into an individual action. What you'll see is that this action is a select. It's a database query that takes as input a particular query object. Okay, in this case, owner equals UID and this subquery, which subquery checks if the level should be public and so on. And finally, each of these query objects themselves are made up of smaller primitives, these fields like owner and level, which correspond to sort of database fields or columns, which are glued together with these combinators like equals and so on and so forth. So what we're going to do in Storm is to exploit this structure. So we're going to look at these central types, field, queries, action, servers, and the functions that allow you to go from fields to queries, from queries to actions, and then build up the whole server. And we're going to associate refinement types with all of these individual elements to build up a refinement typed API such that just by type checking your server code, you can be guaranteed that your security policy holds at compile time. So there's three elements that I'm going to describe. First, I'll give you a whirlwind overview of refinement types. Then I'll describe how we do this information flow tracking or this policy tracking inside these action computations in the server. And finally, I'll explain how we actually connect that with the policies and the database. So let's jump in and look at refinement type checking. So a refinement type is nothing but a plain Haskell type like int or bool or string or so on, decorated with a logical predicate. So for example, this particular refinement type nat is just an alias for the set of integers x such that they are non-negative. Okay? Now you can take these types and you can compose them with arrows and type constructors and so on to get interesting contracts. For example, this function type describes a contract which says that the function must be given inputs that are non-negative and returns as outputs values that are greater than this input x, which is the thing that we named in the input precondition. So this is what is called a dependent type. Now let's see how we go about checking such types. So imagine I wrote a function called double that takes x and returns 2 times x, and I want to check that it has this particular type, non-negative to values that are greater than the input. The way this works, roughly speaking, is that we generate a logical formula which we then ship off to an SMT solver, a decision procedure that will tell us whether or not the formula holds, and if so, the program type checks. So in this case, the formula looks something like, when x is greater than 0, any value that's equal to 2 times x must also be greater than x. And the SMT solver says yes, and so this code is correct. Now let's see how we use these refinement types to sort of track how information flows, how these policies, how security sort of can be checked inside these server computations. The central idea is this notion of authorizees and observers. Okay, so let me again explain with an example. So recall our show wishes server or controller. The set of authorizees of a computation is the set of users who are authorized by the security policy to access the data that that computation touches. Okay, so for example, let's look at this computation. The set of authorizees is the singleton set comprising UID. Why? Because the policy said that only the user should be allowed to access the title unless the wishes are marked public. Here, these wishes are all the wishes, not just the ones marked public. And so the authorizees of this computation is just the singleton set U equals UID. Notice how we're going to represent these sets as logical predicates, as refinements, essentially. U equals UID. Dually, the observers of a computation are the set of users who are provided access to data by that computation. So for example, if we look at this computation respond titles, the set of observers is the session user. Again, just a singleton set because that's who this response goes out to. And so the observers can be the set of the session user. To enforce the policy, what we want to make sure is whenever we sequence 2 computations, the set of observers of the second computation must be contained in the set of authorizees of the first. Why? Because if this containment does not hold, we're essentially leaking information to some observer who is not in the set that was authorized to view the results of the first of the prequel. And so this observer might see some sensitive data that they were not allowed to access by the prequel. So in this case, this policy enforcement fails. Why? Because the observers are the session user, U equals session user, and the authorizee is U equals the user ID. And again, this inclusion does not hold. In our case, this inclusion becomes a logical implication, and we ask the SMT solver, hey, if u is equal to session user, does that imply u equals user ID? And the SMT solver says, no, these might be different people, and so this code is rejected. However, when we fix our code, the equation changes. Now the set of authorizees, since we have added this conjunct level equals public, and the set of observers remains the same. Okay, so the set of authorizees is now the set of all the users. Why? Because we've put in this conjunct level equals public. The set of observers remains the same. It's still just the session user. And now when we ask the SMT solver, hey, if u equals session user, does that imply the set of authorizees? The answer is trivially true, because the authorizees is everybody. So what we are going to do in the Storm framework is to encode this notion of authorizees and observers inside as effects inside this action monad. And so we're going to track the set of authorizees and observers as we build up these computations, and we're going to enforce these checks across the entire server. Let's see how we do that. So first of all, you will have noticed, since it's a do block, each of these yellow snippets is just a monadic computation yielding a t value. So I'm going to call that an action of t. But now I'm going to take this plain old action, and I'm going to refine it. I'm going to index it with these security effects, okay? One refinement for the authorizees, shown in green, and a separate refinement for the observers, shown in blue. So let's look at some concrete examples in the API, just to build up an intuition. Let's look at the respond function. So this takes a piece of text and returns just an action returning unit, but the authorizees are going to be the set of all users. Why? Because respond doesn't touch the database. So it doesn't depend on any sensitive data. All users can have access to that particular data. However, the data is provided to the session user, and so the observers is u equals session user. Let's look at another example. The return function, this plain old monadic return, takes an A as an input, returns an action of A as output, but the authorizees is again the set of all users, as we don't touch any sensitive data, and the observers is the empty set, because we don't send any data to anybody either. The interesting work happens inside the bind operator. Okay, so this is the classic bind signature, action of A to action B, and returns an action of B. All of these are going to be indexed by the authorizees and observers of the first action, the authorizees and observers of the second action, and the authorizees and the observers of the output, the sequenced action. But we're going to add these extra constraints to these refinements via the notion of refinement bounds, which are essentially going to check that the authorizees of the first action contain the observers of the second action. Okay, so the policy is enforced at each sequencing. Second, we are going to make sure that when we sequence the actions, the authorizees of the resulting of the output action is the conjunction, the intersection of the authorizees of each of the two actions being sequenced, because now we're depending on both their data. And finally, we're going to make sure that the set of output observers is the union, because of course we have sent outputs either to O1 or to O2. Okay, so that's how we take these, we sort of track authorizees and observers as effects and build up our server computations and make sure that the observers are contained inside the authorizees at each step. Now we come to the last piece of the puzzle. How do we track the policies which were declared as part of the database schema across the query construction and execution API in order to determine the authorizees for all the primitive actions that involve the database? We're going to follow a three-step approach. First, what we're going to do is we're going to inject the policy predicates as they were specified in the database schema, and we're going to attach them with the field values that the ORM gives us to represent the individual fields of the database, the individual columns of the database. Next, as we build a query using equals and other such query combinators, we are going to aggregate the policies of all the subparts of the subqueries to compute the policies, that is to say, who is authorized to view the results of each query. Finally, when we execute the query by invoking a database select or project or join operation, we're going to use the sort of aggregate policies to determine who the authorizees are for the corresponding action. Okay, so let's see how we inject the policies into the database fields. First of all, recall that the way that we specify the database schema was we specify individual tables like user and wish. And for each table, we specify for each row what the different columns or fields are for that row. So the name, for example, the user has a name, which is a string, and an email, which is a string. The wish has an owner, title, and level, which are respectively user ID, string, and string. An ORM like persistent, Haskell's persistence, which is widely used, generates field values for each of these elements from the database schema. So name, email, owner, title, and level are all first-class fields. And the type of each field is a field row val, where row denotes the table that it's a field of. So for example, owner is a field of the wish table and has the type user ID. Its value has the type user ID. Similarly, title is also a field of wish and has the type string. What we're going to do in Storm is to refine this field data type with the policies, the authorizees, who is allowed to see that particular field, and crucially, also a type level representation of the particular value that that field represents. Let's look at a concrete example. So the title field, which was just a field of the wish table of type string, is now going to be indexed with two predicates. First, the policy for that particular title, which was, if you recall, for any row and for any user, a user is allowed to view that particular row if either the owner of that row is the user owns the row, or the level of that row is public. Okay, and so that's what these green bits, they're taken directly from the database schema policy specification. The blue bits are type level representations of the value of that particular field. For example, what this predicate says is, for any row, the value v of the field is equal to the title of that row, R. Okay, similarly for owner, the value v is equal to the owner of the row. For any level, the value v is equal to the level of the corresponding row. Next, what we're going to do is propagate these particular policies and representation invariants across as we build up queries. So in persistent, the way we represent a query is, again, that has a special type called query of R, where R is the table that query is for. And so what we're going to do is we are now going to refine the types of equals and so on and so forth to essentially further refine the type of query with who is allowed to access its results. So specifically, we're going to index query with two predicates, one called Paul, much like the Paul for the field, which denotes the authorizees, who is allowed to see the results of this query. And we're going to get this from the sub-queries of that particular query. And second, an invariant that describes all the rows that are returned by that particular query. For example, does this query return rows that are public or private or whatnot? And our API for equals and less than and or and so on and so forth carefully track the policies and invariants of the subqueries to build up the policies and invariants for the superqueries. The last piece is the extract function. So how do we actually extricate the policies from the queries to determine the authorizees of the particular database action? For example, let's look at the select operator that takes a query and returns an action, where the action yields the list of rows that correspond to that match that particular database query. As before, we're now going to have refinements, right? So the query was refined with a policy and an invariant that denoted which kinds of records are returned by the query. And the action is going to be indexed by some authorizees, and it doesn't actually directly produce any values to the output, doesn't respond to users. And so these observers are just the empty set. But we are going to add a constraint, one of those refinement bound constraints, that's going to make sure that a particular relationship holds between the invariant, the auth predicate, and the policy. Specifically, we are going to require that all the rows that satisfies the invariant are authorized as long as they satisfy the particular policy corresponding to the query. Okay, so the important bit here is that all the rows need not be viewable, just those rows that actually satisfy the invariant and therefore may be returned by the query. So that's it. This is our API that essentially tracks the database, the policies as they are specified in the database schema, and brings them all the way into the database action by tracking how the policies are aggregated across query combinators and query execution. And finally, when we glue that together with the effect system that we described earlier for bind and return, we get a type for the server. And when we put the whole thing together, we get an end-to-end guarantee that the servers always adhere to the declaratively specified policies. This concludes this whirlwind overview of the Storm Web Framework. If you'll want to learn more, I suggest you check out this particular URL, stormframework.github.io.